welcome to this 11th lecture in this physics of materials lecture series. In the past few classes we have developed the Drude model and examined in what ways it is successful, in what predictions it is successful, and also we have identified some of its weaknesses. Specifically in the last class we spent our time looking at several of the values associated, the kinds of numbers associated with the Drude model in terms of what predictions it makes and how those numbers come about and so on. And so we put down a lot of numbers, and for example we recognize that the specifically the electronic mean square velocity is being under predicted by a factor of 100, and the specific heat at constant volume is being over predicted by a factor of 100. So these are when you come down to values, these are two places, two critical places where the Drude model seems to have some difficulty giving us a prediction. So we finished off saying that we need to examine the kinds of assumptions that have gone into the Drude model, the basic underlying theory that hides behind the Drude model, to see exactly at what stage we have made a mistake, okay, or the model has made a mistake. And from there try to and based on that finding and based on that understanding, we can then see if there is a manner of creating a refined model, so to speak. This is of course been done in the past. We are just going over this process as we rediscover this whole process as we go through their journey again. So this is the basic idea, and so today what we will do is we will examine our system, the kind of system that we are dealing with. We will examine it in greater detail. Let us look at what is the approach that would make sense for that kind of a system, what are typical ways in which such systems are handled when you look at the literature or look at textbooks and so on, and from there we will in fact we will look at we will develop this general idea of statistical mechanics. So by the time we are done with this class, we will have mentioned this area of study, and then also at least briefly understood what it is all about. Okay, so this is what we are going to do. We will touch upon different aspects of how we are approaching this work and what are some nuances associated with it as we go forward through this class. So they will all add up eventually at a given point in time. Each is an independent piece of information which eventually adds up. So you have to take it in that spirit and follow the discussion as we go along. Okay, so let us examine our system, and also keep in mind that we will also see how people go about handling such systems, and therefore I will start there. Specifically I want to draw your attention to one detail which you will stumble upon as you look through various textbooks, but it may not be immediately apparent to you why it is so. So I would like to take a moment to explain that to you before we get started with our discussion. So the point I wish to make is, if you look at the kind of analysis we have done, especially say the kinetic theory of gas kind of analysis, you will find there are approaches to handling these kinds of systems which you will see in say chemistry books, you will see in metallurgy books, you will also see in physics books. So especially where we are bordering on the thermodynamics of the system in terms of our discussion, you will find that all these books have discussion related to large systems, so to speak. Okay, so it may be the system may not be exactly the same, it may be different systems in each case, but large system meaning a system containing a huge number of particles. So that is the basic framework of the system that we are dealing with. What you will find is in a typical chemistry book or in a typical chemical engineering book, you are likely to find that the systems are discussed and analyzed under conditions of constant temperature and pressure. Okay, constant temperature and constant pressure. This is the kind of experimental condition under which the systems are analyzed and discussed in most books in chemical engineering, chemistry, and so on. So this is what you will see. If you look at books in metallurgical engineering, you will find that in fact often again say metallurgical thermodynamics, if you look at it, you will again find that the same constant temperature and pressure are used. So this is chemistry, I am generalizing here. So, it is not that as I finish this I will highlight that once again. I am doing some bit of generalization, but generally speaking this is what you will look at. In metallurgical engineering you will also see the same kind of constant temperature and constant pressure. But more specifically the pressure will often be 1 atmosphere. Okay. So, not just is the pressure constant, it is constant at 1 atmosphere typically. This is all generalization, whatever I am describing to you, I mean there are lots of exceptions to this, but in general you will find this to be the case. Now, if you come into physics, okay, so in physics kind of books you will find constant temperature and constant volume in physics. Okay. So, books that are essentially trying to describe the kinds of systems that we are dealing with, if they are from a physics background aimed at physics students, you will often find constant temperature, constant volume being used. If it is aimed at chemistry and chemical engineering students, often it will be constant temperature and pressure that is used, and if it is aimed at metallurgical engineering students, it will still be constant temperature and pressure typically, but over and above that, that constant pressure will be 1 atmosphere. Okay. So, the reason for this is something as follows. If you look at chemistry and chemical engineering, often the discussion is based on experimental findings and analysis of those experimental findings, and trying to create new situations where they can create some specific compounds and so on. So, for example, if they were looking at if you are looking at refining oil and how you would separate the various fractions, all those kinds of discussions are situations where you have a physical system that you actually have to directly handle, and you have to put experimental controls on it. Okay. So, when you talk of a physical system and you want to actually put experimental controls on it, constant temperature and constant pressure are much easier to impose on a system from an experimental perspective. You can apply constant pressure very easily on most systems. You can generate a experiment where the pressure is constant quite easily in most cases. Okay. So, therefore, from an experimental perspective, constant pressure is the approach to take, which makes the process convenient. Okay. So, this is what is being done in most of chemistry and chemical engineering. So, that is why this is being chosen. In metallurgical engineering, you are often talking of solid metals, you are talking of liquid melts and so on, and that is typically open to some atmosphere. In fact, if you are talking of a solid object, it may be even open to air, so to speak. So, at that point in time, the general pressure that the system is facing is anyway 1 atmosphere. Okay. So, we are looking at large melts and so on, so it becomes a bit difficult to pressurize the system. So, therefore, it is just left to face the atmospheric pressure. So, that is the general situation. So, again it is an experimental system in the sense that there is a physical system, you can actually see the system, you can see what is going on in the process subject to some some safety requirements, but basically you can see the process. It is something that is physically occurring, and therefore an experimental limitation is what is being reflected in the form of the temperature and pressure being chosen as the parameters that you will hold constant for the system as you try to study the system. So, that is what is being done, and in the metallurgical system, since it is typically handling looking up or facing an 1 atmosphere pressure from our natural atmosphere around us, you end up finding 1 atmosphere to be the case. In fact, there are diagrams where the assumption is already 1 atmosphere. Okay. So, many of the phase diagrams that you will see associated with metallurgical engineering systems, you will only see temperature and composition in that phase diagram most often. Okay. You can generate at other conditions also, but typically you will see temperature versus composition, and the assumption is that or it will be stated somewhere, of course, that the diagram has been made at 1 atmosphere. Okay. So, you could have done it at some other pressure if you had wanted to, but in general it is going to be done at 1 atmosphere. So, a large amount of the database that you will come across in metallurgical engineering will be temperature, constant temperature, constant pressure, with the pressure being 1 atmosphere. So, that leaves us with the physics approach. So, our question therefore is, if all of these people tend to stick to constant temperature and constant pressure, why would the physicists choose constant temperature, constant volume instead? Okay. So by the way, in all this discussion, the underlying idea is that when you try to study the system, certain number of parameters you have to hold constant, and within that framework is where you study the system. Okay. So only then the system reaches an equilibrium and you are able to study that system. So and in generally it turns out that you need to hold at least 2 parameters constant. So this is why it's temperature and pressure, and in this case it is temperature and volume. Okay. The reason is in the typical physics book typically that you take, the discussion is about a theoretical framework for the process that you are dealing with. Okay. So a theoretical framework for the concept that you are dealing with, for the process that you are trying to describe and so on. So now for theoretical understanding, or to develop a model or to develop equations for the system, it is very important to know what are the energy levels available in the system. Okay. So that becomes a very important consideration. You should be able to say clearly that these are the energy levels that are available within the system. Once you know the energy levels, then you can do further theoretical calculations, and theoretical considerations can be put into place to see how those energy levels are filled, and therefore say something about the system. So it is very fundamental that you should know what are the energy levels. You should be able to say that. Okay. What happens, which is something we will get back to much later in our course, several classes down the line we will look at it in greater detail, but the basic idea is that when you have a constant volume system, when the volume is constant, the energy levels are identifiable. Okay. So it is if the volume were not constant, if the volume changed from moment to moment, the energy levels also keep changing, the allowed energy levels keep changing. Okay. So therefore if you want to develop a theoretical framework or theoretical understanding of the system, or develop a theory for the system, constant volume becomes very important. Okay. Because the constant volume ensures that you understand what are the energy levels within the system, and once you understand that, you can then go about filling it up in various ways and then saying something about the system. Therefore from a theoretical perspective, when you want to make calculations that reflect the theory behind how the system is working, you end up having to choose constant temperature and constant volume as the defining characteristics of the system within which you are actually developing the framework. Okay. So therefore this is the difference you see between the kind of information and discussions that you will see in books in chemistry, chemical engineering, metallurgical engineering, and in physics. Okay. Now just 2 more comments I will add on this before we proceed. The first thing, the most important thing I would say at this stage is that this does not mean they are talking of something totally different. Okay. It is not. So we are actually looking at a system which shows it's the to describe it, it is something like this. You have some kind of a surface which contains all the properties of the system reflected in some kind of a surface. We are just looking at if you are looking at it from the perspective of chemical engineering or chemistry or metallurgical engineering, you are looking at one point on the surface. If you are looking at it from the physics perspective of constant volume, you are looking at another point on the same surface, but you are still describing the same surface. That is the way to look at it. You are still describing the same system, the same surface, you are just looking at it from 2 different perspectives. So the final set of things that you will say about the system should end up being the same. Okay. It's as simple as looking a mountain from one side or from another side, that's it. It's the same mountain, so you are going to say the same things about the same mountain. Okay. So or you may give some new understanding to the mountain, but principally there is no disputing the fact that you are talking of the same thing. Okay. So therefore these 2 approaches, even though they are using different variables and holding them putting constraints on different variables, they are essentially talking of the same system, and they will end up giving you the same description. I mean, at the end of the day, your final results are not going to be diametrically opposite or different in any fundamental sense, because that they have chosen this. Okay. So so that is the thing that I want to highlight. Also the second thing which I want to highlight, which I also just mentioned a little while earlier, but I will state it again here, what I have told you are generalizations. Okay. So there are exceptions, so there is no reason to believe that what I have stated is exactly the way you will always see it in every book that you pick up. Largely this is true, and the reasons I have given you are basically the reasons why this is the case. There are going to be exceptions, but that is how it is. Okay. So this is what it is. So right now our discussions are on the physics of the material. and as you have already experienced from our previous classes, our intent is to develop theoretical understanding of the system, right. So therefore our discussion tends to have the same constant temperature, constant volume as the defining framework. These are the constraints placed on the system, and within the extent of these constraints we describe the system, fine. So we will leave this, I will leave this thought with you for the moment. I just wanted to bring it up now because as we proceed into some of the other discussions, this is somewhere hidden in that discussion. It is not stated upfront at every stage in that discussion. This is hidden somewhere in the discussion. Much later in one of the later classes it will again stand out, but I just wanted to highlight it now so that at least you are aware why that this is there somewhere in the background, rather than being surprised by it at a later stage. Okay, so this is there in the background, that it is constant temperature, constant volume. So I will leave it here, we will come back to this at a little later stage. Now we will come back to discussing our immediate topic, so to speak, which of course is that the Drude model succeeded in some places and failed in some places. So we will look at some of the parameters that are associated with the kind of system we are dealing with, and then in that process we will try to go forward and see what is the detail that we are interested in identifying. The first thing is that the system that we are dealing with is a very large system. Okay. So we have gone through this calculation repeatedly. Just to give you an idea, 1 meter cube of a material is going to have about 10 power 28 atoms or free electrons per unit volume. Okay. So 10 power 28 atoms or 10 power 28 free electrons per unit volume is what 1 meter cube of the system has. Now this is a very large number. Okay, so this is I mean it is immediately apparent it is a large number, but in any case it will become much more apparent to you as we proceed through the class that it is a very large number. As it is clear that it is a large number, but relative to what is the question, so which is what we will look at. So the first thing is we deal with large system, with a large system, and we are trying to say something, about this large system. We want to get some feel for what is this large system doing, how will it respond under different circumstances. So this is the main sort of issue here, that it is a large system. The other thing is we are our discussion, especially when we spoke about the Drude model and did various of the calculations, our discussions at some point revolve around energy. Our discussion revolves around energy associated with the system and how that energy behaves. I mean, in other words, when we talk of specific heat, therefore how is that what is happening when you try to raise the energy or lower the energy and so on. So so there are two things. Okay, and again to immediately link up to what we just discussed, please note that we are talking of energy. So immediately this need for that constant volume gets linked up here, so with whatever we discussed, but we will see it more specifically a little later as a concept. This is where it is getting linked up, that we have energy associated with the system as our primary consideration, plus that it is a theoretical calculation. Those are the two things that we look at. So we want to know energy associated with the system, and that is the case for a very large system. So what we want to see is that what we want to understand of this situation that we are dealing with is that when you look at an energy associated with the system, ultimately it is the energy when you take a system and you heat it or put it at some time, even let us say it is at room temperature. Now the idea that it is at that temperature is something that is that conveys the fact that all the constituents of that material actually have that energy, or on average have that energy. The average energy associated with all the constituents of the system that is held there will be the same, that will correspond to this temperature of that system at that large energy of that large system. Okay, so this is what we are looking at. So now when you look at a large system and you want to say something associated with the energy of the system, what should immediately stand out as a concern or as an issue is that it is not possible for us, it is not physically feasible for us to actually know the exact correct information about each of those 10 power 28 atoms or 10 power 28 electrons. It is simply not physically feasible for us to identify all the details of the 10 power 28 atoms, and then on the basis of all the details we just sum them up if necessary, or we take the average of them if necessary, and so on. So, so that is physically not possible. So we need an approach Okay, so we need an approach that enables us to make statements about the system as a whole without knowing every single detail of the system. Okay, so that is the basic problem that we are dealing with, or the challenge that we are dealing with. We need to have an approach that enables us to make some overall statements about the system which are correct and consistent about that system, but that approach should not require us to know every single detail of every one of those 10 power 28 atoms. Okay, so as the system unfolds, it should automatically give us the averages that we are looking at. Okay, the average behavior of the system should begin to stand out. Okay, so this general approach that we are looking at is what is referred to as statistical mechanics. Okay, so this general approach that we are looking at, which will give us some overall idea of the system without requiring us to have all the intricate details of every single particle that is present within the system, that overall approach is referred to as statistical mechanics. Okay, so what we will do in the rest of the class is I will lead you from a very small system forward, and then let us see if the understanding of a very small system or a few very small systems, we will look at 2 or 3 very small systems, we will see if that understanding from those 2 or 3 small systems gives us some indication of where we can head with a very large system. Okay, and what kind of a generalization we can pull together for a very large system, and that generalization that we can pull together is this statistical mechanics. Okay, is this field of statistical mechanics. So that is what we will do, right. So what we will do is we will look at for this purpose in thermodynamics they talk of what is called a macro state and a micro state. So let us say we have a constant temperature, constant volume, and total energy is fixed at some value which I will call say 3E. Okay, so 3E is the total energy. I am just arbitrarily putting this number down so that we can run through an example. So 3E is the total energy of the system, and you have it is at constant temperature, constant volume, and the total energy is fixed. So we will look at 3 examples of small systems which could be placed under these constraints, and we will see what is the general statement we can make about such systems. Okay. So let me just say that let us say that the system, because it has constant volume, and as I said we will discuss that later, because it has constant volume it has fixed energy levels is a statement we will just arbitrarily make for the moment. and we will say that those energy levels are 0, E, 2E and 3E. Okay, so these are energy levels. So this is energy. So this is energy, these are energy levels that are available in the system because it is because of the constraints that have been placed on the system. We will look at 3 possible small systems and see how they can handle these constraints. The constant volume and temperature have already resulted in the total energy and the energy levels, and the total energy value is 3E. So all these constraints are now placed here. We will look at a possibility that the system consists of just 2 particles. Let us say it has 3 particles, and we will look at a case where it has 4 particles. Okay, so we will just look at 3 possible cases, 2 particles, 3 particles and 4 particles being present in the system, and these are the energy levels available to that system, fine. So let us look at this. Now let us take 2 particles, we will put these energy levels back here. So this is 0, E, 2E, 3E. Incidentally, I also want to draw your attention to one additional detail here. The fact that it is constant temperature, constant volume and the total energy is 3E, that combination is referred to as a macro state for the system. Okay, so that combination, that overall combination for the system is that macro state. Now we can arrange these 2 particles, let us say we are now only going to discuss 2 particles, the 2 particles can be arranged in various different ways within these energy levels to be consistent with this overall macro state. Each way in which you can arrange those 2 particles becomes called gets to be called as a micro state. Okay, so we will what I am going to put down there will be 2 different micro states which are consistent with the same macro state. Okay, so for example we have 2 particles and we know that we need a total energy of 3E. So what are the options? One option is you have a particle at 3E and the other particle sitting at 0. This is one option available to you. Okay, so this is particle, so these are the particles. Okay, so this is at one is at 0, one is at 3E. The other possibility is that one particle sits at 2E and the other particle sits at E. So this is one possibility. So this would be considered as one microstate where you have one particle sitting at 3E, one particle sitting at 0. This is another microstate where one particle is at 2E and another particle is at E. Okay, so this is the thing. If you swap these particles, it does not matter, this is still the same microstate. If you similarly you swap these 2 particles, it does not matter, it is the same microstate. So so this is the in the sense that at least it is a different situation, but it is the same state, I mean same microstate is what I am saying. So now what are the ways in which you can accomplish this? Basically if you look at the if you put it down in terms of factorials, which we will just do for the moment, there are 2 particles, so you could accomplish this in 2 factorial ways, of which there is one particle of one kind in 3E and the one particle of the same kind in 0. So we would say 2 factorial by 1 factorial by 1 factorial. For now you just assume that this is correct. When we look at alternate possibilities, the details of this kind of an analysis will come out, but simply if you take 2 particles and you have these energy levels, this is the way in which you could accomplish this. Okay, so so in other words you could do this in 2 ways, which is fine. You could either have and incidentally these particles we will also call them when we do it like this, when we do this kind of an analysis, when we approach the problem the way we are doing it, what is true about those particles is that they are identical but distinguishable. Okay, so they are identical particles but we are able to distinguish between them. That is why when you take this particle and put it up there and you swap them down, you swap these 2 particles around, we call it another state, I mean, or at least we count it as 2 possibilities. Okay, so it is the same microstate but there are 2 ways in which you can arrive at this microstate. Okay, so therefore this is done in 2 ways. The same will be true here. you can do this the same way, 2 factorial by 1 factorial by 1 factorial. So this can also be accomplished in 2 ways. Okay, so both these arrangements can be accomplished in 2 ways given the overriding definition that the particles are identical but distinguishable. Okay, so right now I am putting some terms down which are actually very important terms. When we say identical and distinguishable, there is they mean something very specific. At this moment I will just leave it like this, we will, because our focus is on the calculation. A little further down, maybe in a class or two, maybe in a couple of classes from now, we will actually come back to discussing what is meant by identical, what is meant by distinguishable, and also why it is so important. Why is that? Right now they are just 2 descriptive terms. I mean, it does not seem like any great term out there. Identical and distinguishable are not, do not immediately come across as something of great relevance, but for the purpose of our discussion, in fact for the theories that we develop, you will be very surprised to find that this pair of words is extremely crucial for the body of material that we are studying. Okay, so when we find that the Drude model fails, it will fail because of something that is related to these 2 words, and the alternate models that we will pick up which will actually do well will again have to do with the fundamental reason why they will be doing well will have to do with how they are handling these 2 terms, okay, or how, what do these terms represent in those systems or in those models. Okay, so right now these are just 2 words. I will leave them here for now because that is not the purpose of our immediate discussion. We will come back to it later. In fact in 2 classes we will be back at this these 2 terms. So for the moment it is enough that we find this discussion, we find they are identical particles. So this is the same microstate as if you were to reverse it. So we will call them, we will therefore treat them as being under the same microstate, but they are distinguishable. Therefore if you shift that one down and shift this one up there, it is counted as a second possibility, as 2 ways in which you can accomplish this microstate, right. So both of them are consistent with this description. So you have 2 ways to do this, 2 ways to do that. Okay, so if you randomly look at the system, you randomly take a snapshot of the system, there is 50% probability that the system is sitting in this condition, and there is 50% probability that it is sitting in this condition, because you have 2 and 2, that is it, there is no specific preference and so on. So there is a 50% chance that you will the macro state of the system the macro state of the system is fixed, there is no change in the macro state. Okay, the macro state is everything that I just described, constant temperature, constant volume, and total energy being 3E. So that is all fixed. So that is fixed, but which micro state you will find it in? Will you find the particles being at E and 2E, or will you find it at 0 and 3? Those are the 2 possibilities that you have, and since both of them can be arrived at, there are basically the same number of ways in which you can accomplish both of them. There is a 50% chance you will see it in this microstate, and 50% chance that you will see it in that microstate. All right. So also to put it down as a ratio, 1:1 is what we are looking at. 1:1. 1:1 is the ratio of the chances that you will find it in this state or in the other state. Fine. Now the same system, same macro state, we will look at if we have what will happen if we actually have 3 particles in the system. Okay, so we will do that. Okay, so we will look at now the same system, same macro state with 3 particles and see what are the possibilities. So same thing, we will have write the energy levels down here, 0, E, 2E and 3E. Okay, now we have 3 particles available in our system. So we will say 3 particle system. So what are the possibilities? We can once again we can have 2 of the particles sitting at 0, which I represent by these 2 points, and in which case 1 particle sits at E, or I am sorry, 1 particle sits at 3E. So you have 2 particles sitting at 0 and 1 particle sitting at 3. That is one way in which you can get a total energy of 3E. Next possibility is that you have 1 particle at 2E, 1 particle at E and 1 particle at 0. That is one way in which you can accomplish this 3E being your total energy. And the third possibility is all the 3 particles are sitting at E. Okay, so these are 3 possibilities that you have. Okay, so this is one possibility, this is another possibility, and this is the third possibility. So these are three different microstates corresponding to the same macro state, that is the to use our terminology, that is what we are looking at, fine. So now how many ways can we accomplish this, this and this is the question that we need to ask ourselves. So if you look at it here, this is 3 factorial, there are 3 particles, so you select them in 3 factorial ways, in which in one place we have only one particle, so it is 1 factorial there, and in this energy level there are 2 particles, so there is 2 factorial ways in which you can rearrange them and still be the same. So just swapping them around in the same energy level does not count, so that is why it ends up at this. So if you look at it, this works out to 3, in 3 ways you can accomplish this, right. So and you can also see effectively it means one particle here, you can move the next particle there or the third particle there, so that is the way in which you would do it. Now if you look at this arrangement, there are 3 ways in which you can pick this particle, there are 2 ways in which you can pick this particle, there is only one way in which you can pick this particle if you want to look at it that way, or if you want to put it down in this notation, you have essentially 3 factorial by 1 factorial, 1 factorial and 1 factorial, okay. So that is essentially 3 factorial, that is the same thing as 3, 2 and 1, that is what I just described to you. 3 ways you can pick this, 2 ways you can pick this, 1 way you can pick this. So therefore this works out, there are 6 ways in which you can make put these particles here, right. So there are 6 possible ways in which you can keep rearranging these particles such that each is a different arrangement, is unique because the particles are distinguishable, they are identical but they are distinguishable. So moving this particle up in energy level and moving that particle down in energy level is considered as a new way in which you can accomplish the same microstate, whereas here they are at the same energy level, therefore swapping them does not count, that is the only difference, okay. So so this is the thing, there are 6 ways in which you can accomplish this. Now all the 3 particles are sitting at the same energy level, there is only one way you can do it because there are only 3 particles. If all of them are sitting at the same energy level, there is no further arrangement that you can do because they are at the same energy level, even if they are distinguishable, just rotating them around at the same energy level makes no difference, the system is still in the same state. So this is this microstate can be arrived at in only one way, okay. So or if you want to put it down in factorial analysis, it is simply 3 factorial by 3 factorial because 3 are there in the same energy level, so this occurs once. So with 3 particles we find that this macro state of the system can be accomplished using 3 different microstates as opposed to 2 different microstates that we saw there, and amongst these microstates we find that one of the microstates can be arrived at 3 times in 3 different ways, the other microstate can be arrived at in 6 different ways, and the third microstate can be arrived at only once in one form. So if you want to put it down as percentages, if you take a snapshot of the system, and we will say that in all these cases in our discussion upfront there is no preference for a given microstate, it is a completely random system, it only has these overall constraints placed on it. So at a given moment it could be in any one of these microstates equally happily, okay. So there is nothing that upfront tells the system that no you should stick to this microstate, that is not the way it is. Only the overall constraints placed on the system which define the macro state are actually valid. Within that as long as the system is consistent with the macro state, it is equally possible that it is at that state, okay. So now that only leaves us with the possibility of the fact that one of the microstates can be arrived at in many different ways, therefore you are more likely to see the system in that particular microstate if you take a snapshot of the system, which is basically what we are looking at here. If you randomly look at the system and assume that any one of these states is equally probable, then 30% of the time you will find that it is in this microstate because it is available to us 3 times, 30% it is going to be available here, 60% it will be available here, and 10% it will be available here, okay. So 10% of the time you will find it in this microstate, 60% of the time you will find it in this microstate, and 30% of the time you will find it in this microstate. If you wish to take a ratio again, you will find this is now 1, okay, especially we will take a ratio of only the top 2 because that gives us that is information that is more useful to us. So if you look at the top 2, it is 1:2, the most 2 probable cases if I want to look at, okay. With respect to 10 it is going to be even larger, so it is 1:6 whatever 3, 1:6:3 between, or if you want we can put that also down, it is 3:6 is to 1. So 1 is to 6 is to 3, amongst the top 2 that is 1 is to 2. Okay. So in other words, in this discussion we find that the microstates are not equally probable. There is one microstate that is more probable because it is at 60%. Okay. So, so there is a microstate that is more probable, and that is twice as probable as the next most probable microstate. Okay. So this is the most probable microstate, this is the next most probable microstate, this is the least probable microstate. The most probable microstate is twice as probable as the next most probable state, right. So moving from 2 particles, when we move to 3 particles, first of all we find that the probability of occurrence of a microstate now begins to differ. We find that each of the microstates has a different probability of existence, and on top of it we find that there is one microstate which is distinctly more probable than the other microstates. In fact, even now we find that this microstate is actually more probable than the other 2 microstates combined, but that is something we will look at as a next step. But more importantly, this is twice as probable as the next most probable state. Okay. So we will just go one more step, we will take 4 particles and then we will make some generalizations. So same system we will take, same energy levels 0, E, 2E and 3E. We will say there are 4 particles available to us, so 4 particle system. Right, and the same considerations in terms of the macro system, macro state. So what do we have? We can have one state where you have one particle here and 3 sitting here. This is one way in which you can accomplish 3E. Another possibility is you have a particle at 2E, one particle at E and 2 particles at 0. The third possibility is you have 3 particles at E and 1 particle at 0. Okay. So these are 3 possible arrangements given the these are the only 3 possible arrangements that you can think of. You can't have more than 1 particle in 2E because then the energy of the system is more than the 3E limit that you have. So you can never have 2 particles there or 2 particles here, maximum you can have is 1 particle, and then that leaves you with the other systems again, other energy levels. Again, if you have 1 particle here, you can only have 1 here at most, you can't have anything more, and then if you have 3, this is what you will have. So these are the only ways in which you can arrive at the system subject to the constraints that we have. Now let us look at the number of ways this microstate can be accomplished. Since you have only 1 here and 3 here, essentially it is 4 factorial by 1 factorial times 3 factorial. So there is essentially 4 ways, and even otherwise you can see you have 1 and you have 3, so you can rotate them around, each particle can be brought up here once, so therefore there are 4 particles, therefore there are 4 ways in which you can do this. Done. So same thing we will do here, this will come out to 4 factorial divided by 1 factorial, 1 factorial and 2 factorial, right. So this is simply 4 into 3, that is 12. So there are 12 ways in which you can accomplish this microstate, and if you come to the last one, it is actually sort of an inverse of this in terms of the number of ways, in terms of the way the arrangement is. Here we have 3 at the higher energy level, 1 at the lower energy level, but in terms of number of ways in which you can accomplish it, it is the same. There you can rotate this energy level around 4 times. So again you will have the same thing, 4 factorial by 3 factorial times 1 factorial. So again you will accomplish this 4 times. Okay, as I mentioned, you know, this one can be rotated around, so you can get 1 by 1 out here, the others will go back there. So we have 4 is to 12 is to 4, right. So if you put down as a probability, so if you actually count them up, this will work out to out of 20. So in terms of percentages, this is 60%, this is 20%, and this is 20%. Same comment will hold as before, that is each individual microstate is equally probable. So simply because this microstate can be arrived at in 12 different ways, at a given instant if you just randomly look at the system, there is a greater chance that it will be in this microstate. That is all we are talking, that is all we are saying, and so in terms of a ratio this is 1 is to 3 is to 1, right. So we have now looked at this, we have looked at a very small system and we have gradually added particles to it. We started with 2 particles, then we made it 3 particles, and we made it 4 particles. What we find is as the particles, number of particles in the system increase, one concept that begins to arrive or immediately arrives is that the microstates are now no longer equally probable. There is one microstate that seems to be more probable than the rest of them. Okay, so so there is a more probable microstate, so that begins to stand out in the system, and we also find that in general the tendency is that the more probable microstate, the probability associated with it seems to go up, or at least in relation to the other microstates that are available. Reason being, when we first started with 2 particles, the ratio between the 2 possible microstates was 1:1. When we made it a 3 particle system, the most probable microstate was twice as probable as the next most probable state. When we put 4 particles in, it became 3 times as probable as the next most probable state. Okay, so 1:1 became 2:1 became 3:1, fine. So this is what we are seeing in the simplified set of examples that we have taken. Okay, so I am not saying if you exactly go about this, you add one more particle, it will proceed in exactly precisely the way in which I have described it, but the general trend is going to hold. The general trend is going to be that as you add more and more particles to your system, the most probable state will become more and more probable. Okay, so please remember that these are all like 1 particle, 2 particle, 3 particle, I mean sorry 2 particle, 3 particle and 4 particle systems that we have looked at. We started the class by highlighting the fact that the systems that we are talking of have 10 power 28 particles. Okay, so that is a huge number, that is so many orders of magnitude, 28 orders of magnitude away from what we are talking of here. Okay, so the comparison is in scale is like huge, there is no, I mean it is just completely out of scale with respect to what we have discussed here. So what is seen is that when you go to such very large numbers of particles in a system, this small trend that we have seen here, that small trend that we have seen here, which is that there is a microstate which is more probable than the other microstates and seems to be getting more and more probable, that small trend that we have seen is amplified in a very huge way. Okay, so what happens there is that we have a bunch of microstates, a whole bunch of microstates that are possible for the system, but there is one microstate which is the most probable microstate, but the number of ways in which you can arrive at that microstate is very very significantly higher than even the next most probable microstate. Okay, so we will put that down. Okay, so the statement is this: as the number of particles in the system increases, the most probable microstate of the system becomes more probable than all of the other microstates combined. Okay, so this is a very important statement and it is very relevant with respect to the fact that the number of particles has increased. Okay, so only under those constraints, we spoke about one of 2 particles, 3 particles and 4 particles. From there we have made a leap to 10 power 28 particles. When you move from such a small system of 2, 4, 3 and 4 particles to 10 power 28 particles, the most probable microstate, all the other concepts are still the same, that there is an overall macrostate and corresponding to that macrostate you can have several microstates. The most probable microstate will be one where its probability of occurrence will be way higher than all of the other microstates combined. Okay, I just showed you that the most probable microstate is twice as probable as the next most probable state and then thrice as probable as the next most probable microstate. So we are only talking of factor of 2 and factor of 3 with respect to the immediately next most probable microstate in the examples that we considered. I am saying that when you move it up to 10 power 28 particles, you reach a state, you reach a situation where the most probable microstate completely swamps the probability of all of the other microstates combined, not just the second one alone. I am saying the second, third, fourth, fifth possible microstates, you combine all of them, their probability of occurrence will be tiny compared to the probability of occurrence of the most probable microstate. So you can also sort of imagine this. You may ask how that happens and all that. While I have shown you a small trend and so on, please note that in all these cases we are talking of factorials. Okay, so on top of the on the numerator we may have all of the particles in the system, say nf factorial you may have, right, and in the bottom you will have several factorials which are also very large numbers. Okay, so you will have whatever n1 factorial, n2 factorial and so on. This is again I am just generalizing to give you a hold on where this issue might come up with. So when we are talking of very large numbers, if one of these factorials disappears and everything else stays common between the various situations that you are considering, just the disappearance of one factorial simply because it is a huge number will change the ratio of this with respect to the immediately next probable system by many orders of magnitude. Okay. So that is where this issue comes up from. That is the crux of this idea, and that is where this situation arises where as the number of particles increases, the most probable microstate of the system becomes more probable than all of the other microstates. Please remember this, it is all of the other microstates combined, not just the second most probable microstate, all of the other microstates combined. Okay, so statistical mechanics is a field of study where it looks at this situation, okay, and it says that the equilibrium state of a system is the most probable state of the system. That is the basic idea of statistical mechanics. It says equilibrium state of the system okay, equilibrium state of the system is the most probable state. I want again emphasize that there are other states, other possible states. It is simply that the most probable state is almost like 99.99% chance that you will find it, or even more 99.9999% chance that you will find it in the most probable state. Therefore for all practical purposes that is the equilibrium state of the system. You go at any given point in time, you try and look at the system, that is the state you will find the system in. So the equilibrium state is the most probable state, and statistical mechanics works on this principle. It looks at large systems where because of the nature of the system the equilibrium state is the most probable state, and statistical mechanics provides you with all the tools of getting you the properties of the most probable state. Okay, so this is the general idea. Okay, so it is with this theme or this concept in mind that I would like to halt this class and just re-emphasize that as we go forward we will look at the system again, or the system that we have dealt with again, except that we will now introduce the concept of statistical mechanics into the system and try to identify the most probable state of our system, which is what we used, and therefore try to understand the properties of the system on the basis of our recognizing what is the most probable state of the system and therefore the equilibrium state of the system. When we are able to do that, we find that we can extract information about properties of the system without knowing the details of every single particle within the system, and that is the basic goal of our analysis, because once we do that we can say something about the v square values, mean square velocities values in the system. We can say something about the specific heat of the at constant volume of the system as for the whole system without knowing the details of every single particle, and therefore we are now able to actually make some scientific statements about why the CVE value has ended up as what it has ended up at, and why the v square value has ended up at what it has ended up at, and therefore have a good understanding as to where the errors of the Drude model come from, and that would then lead us to the next step, which is how we would go about improving on the model. Okay, so with this we will halt, we will take it up next class, keeping in mind that statistical mechanics will now become the tool that we will use to look at our system. Okay, thank you.